Second force is electromagnetism. As the name suggests, it has to do with both electricity and magnetism. They are one and the same, which we'll talk more about in the second semester. Yes?
Can we add to the Earth's mass?
Yeah.
So does that mean if there's more people, we weigh more?
Well, no. Not if there's more people. Why would that not add to the Earth's mass? Where would that mass come from for the more people?
From the Earth.
From the Earth. Unless the only way to add mass to the Earth is to take the mass from somewhere else and bring it here. So when the astronauts went to the moon and they grabbed samples and they brought them back, we are exactly more massive as the exact amount of samples that they brought back, as long as they didn't leave any of them there. Well, I guess technically they left the lunar module, so we might be less massive. Thanks a lot, guys. Electromagnetism. Electromagnetism is the attraction or repulsion between charges. Negative, 0, positive. Where do we get all of our mass from? Atoms. Where do we get all of our charge from? Specifically within the atoms, it would be the subatomic particles in there. That's where our charge comes from. Typically, objects are neutral. Not to say that they don't have protons and neutrons or electrons, but they have the exact same amount. That doesn't mean they're not working though. I know you know this, but let's just cover it real quick. Attraction would happen between what particles here? Positive and negative, and repulsion would happen between negative, negative, positive, positive. Very good, yeah. So like charges repel, opposites attract. What do the zeros do? Nothing. 100% nothing for electromagnetism. People, of course, often ask the question, then, why are they around? And the reason why they're around is the next two that we'll talk about here in just a second. I assume that you've heard this because when I said it in years past, a lot of people love the conversation so much that they spread it around. But have you heard the conversation that you never actually touch it?
Oh, yeah.
You've never heard it. Well, that's fine. Okay? You told me earlier that when you look at an atom, positives are on the inside, right? Neutrals are in here as well. And what's on the outside? I apologize, I know that's more simplistic than it actually is, because of course electrons don't really exist except they're in a state of probability, which is why they have their nuclei or their orbitals exactly where they do. They don't really exist on the outside, but we're going to go with this simplistic model for right now. Sweet. The question that will hopefully boil your mind later is, if they don't really exist, how do they exert a force? But we'll get to that. No, we won't. Actually, that's later physics. Now,
why can't we just get to it that we found?
Because you've got to build building blocks, dude. You don't get to the top of the Eiffel Tower by just building the top. All right. So, yeah, it's only going to be about a foot off the ground. So, whatever. Okay, so I am made out of atoms, and you are made out of atoms, right? And on the outside of all atoms are what? Electrons. So you can almost imagine on my hand there's a cloud of electrons on the bottom, and there's a cloud of electrons in the desk here too, right? And similar to gravitation, there's two things that matter: how big they are and how close they are. So the closer so I have electrons that are getting close to each other, right? And what happens the closer and closer they get? They repel more and more and more. So for them to touch would require an infinite amount of force. And that just doesn't happen. So actually, when you're sitting on the table like this, or I'm holding myself on the table right now, I'm actually floating on top of the table. Now, the distance between my electrons and the table's electrons is so very, very small that are we going to be able to see it? No. I also have to be very clear on this because I will use the word touch throughout the rest of the year. You have to define the word touch when you say this conversation we don't actually touch anything. By touch, what I mean to say is that the one thing does not make contact or come next to the other. Really what we say when we talk about touch, what you're asking is, okay, why do I feel anything? And that is what touch is. When I get close, I feel the force of that electron pushing up on my electrons, and that is what we define as touch. Another question that a lot of people then have is, what about smooth and rough objects then? Why is one smooth and one rough? It has to do with the layout of those atoms. If the atom or electrons are laid out in like a perfectly smooth shape like that, you're going to feel the object is smooth. On the other hand, if it's more jagged and all over the place, then you're going to feel that the object is rough, because it just drags a little bit more. Questions on that? Now, negatives and negatives are not the only thing happening, right? What else we got? What's that? Protons, right. Protons are in there too, right? What do protons do to negatives? Attract at the exact same time, right? They don't take turns, right? So if you put your hand across the table and you try to slide it across the table, which way does the table pull you? Think about that. Which way does the table pull you?
Opposite the way you're dragging.
Opposite. Why? Any ideas?
Because
I mean, according to my statement before, if this is my hand, it should just repel. What's that? Yeah, positives over here on the inside. And actually over here as well. So what will these positives do to these negatives? Attract. And what will these negatives do to those positives? Attract. That is not to say that both are not happening at the same time. While these are attracting, these are still doing what? Repelling. So you're never going to touch the table, but the table is close enough to have an effect on you. As a matter of fact, all materials that are very close to each other do that exact thing. They all don't touch, but they all hold on to each other pretty darn well, which is why, of course, if you take a sheet of paper and you pull it too quickly, a lot of times you grab another one too, don't you? Because the two sheets of paper are holding on to each other. This force right here is basically your entire last year in chemistry. Covalent bonds, ionic bonds, all you were basically doing is electromagnetism. Covalent bonds is actually what I just described right here. Negatives holding on to positives and negatives holding on to positives. The nucleus of one atom holds on to the electrons of the other and vice versa. Yes?
So when you glue stuff, are you just gluing atoms together? I mean,
Probably the easier thing to look at is actually tape. Okay? Why is tape sticky? Okay? Well, the top side of the tape is smooth. The top side of the tape is smooth because the electrons in my finger and the protons in here can't get a hold of each other very well. And the reason why that would be, is why they can't, and I can't show you a great picture, would be because they just can't get close enough, or there's too many electrons, or the electrons are too smooth, something along those lines on the smooth side. On the other side, the sticky side, for some reason, the electrons and protons can get closer. It always has to do with their shape. And because they can get closer, there's a bigger attraction. And because there's a bigger attraction, that's what sticky is.
what happens when it wears out?
What's that?
Like when it wears out.
When it wears out, you're just ripping away the protons too much. You take away too many of them. I'm taking mass off the piece of tape right now. And if I take away enough mass, it doesn't have any electrons there, or I smooth it out in some particular way, and then it doesn't stick anywhere. It still pulls. It just can't pull the same way as it did before because the shape isn't the same because I removed some of the shape. Okay? All right, now, these two right here are your everyday forces. These are basically the only two you deal with on a day-to-day basis. Everyday forces. Those two right there. Actually, I'll put this arrow back over here. Everything else that I'm going to draw, you don't usually deal with on a day-to-day basis. When you walk around, the reason you walk is electromagnetism. When I push this door, that's electromagnetism.